Okay. All right. So I'm gonna do part of 3.2, and then we'll finish this up tomorrow. Um, so let's talk about some ideas that you're probably already familiar with just a little bit. Okay. So if you look at a regular old parabola, it's nice because the left looks the same as the right. Okay. And so it's what we call symmetric with the y-axis. So that means if you fold it along the y-axis, the right would look the same as the left. Now, if I take this graph and I slide it over here, it's still got an axis of symmetry, but it's not the y-axis. Okay? So there's some symmetry there. Okay. If I take a look at something like this, so let's say I take that function right there, which you probably saw in 1010. It's a cubing function. It looks like that. Okay, are there some things that are similar on the left side and the right side? There are. Okay, but it's not like I can fold it along the y-axis, right? So if I did that, I'd have a piece over here and a piece over there. Okay, and that's not what I've got. Okay, so this has a different type of symmetry. This is called symmetry with the origin. Okay, and symmetry with the origin is different. This is called, so let me erase that one. This is called reflective symmetry or line symmetry. It means if we fold it along the y-axis, the left looks the same as the right. Okay? This is different. This isn't a fold type of symmetry. This is what we call rotational symmetry or point symmetry. So imagine if I put a point right here at the origin and I turned this 180 degrees. So I take this, slide it over here, and take this, slide it over here. If I turned that, put your pencil on the origin and turn it 180 degrees, does it look exactly the same as it did before? Okay. And that's called rotational symmetry or point symmetry with the origin. Okay? So this is an example of symmetry with the y-axis, and this is an example of symmetry with the origin. Okay? And it turns out there are some interesting names for these. Okay? And there are good reasons for them. So here's what this looks like. Okay? So I'm going to go through this example nice and close. So if I have y equals x squared, so let's go ahead and graph that. That's a parabola. So go over from the vertex, over 1 and up 1 squared, over 2 up 2 squared. So it looks like this. Okay. And I'll label a couple of these points. This is 2 comma 4, and this is negative 2 comma 4. Okay. That is symmetric with the y-axis. So negative 2, 4 is on the graph. So is 2, 4. This point here is 1, 1. What's this one over here? Negative 1, 1. Okay? And what mathematicians like to do is we kind of like to generalize. Could I come up with a formula for this? Well, if it's symmetric with the y-axis, this should happen. If xy is on the graph, negative xy should also be on the graph. Like 2, 4 is on the graph, so is negative 2, 4. 1, 1's on the graph, negative 1, 1 is on the graph. The next most convenient point would be 3, 9. Isn't negative 3, 9 on that graph also? Okay, so see what I'm saying here? Okay, and any graph that's symmetric with the y-axis works this way. It doesn't matter whether you go to the left or the right, you get the same function value. So if I go to 2, I get 4. If I go to negative 2, I get 4. Make sense? Okay, so what this means is f of negative x is exactly the same as f of x. So if you plug in a negative x, you get exactly the same as if you plugged in a positive x. So for example, on this one, is f of 2 the same as, f of negative 2, is it the same as f of positive 2? Yes. It is, you get the same y value out. Okay, this has a name. It is called an even function. So if I ever say, hey, we're working with an even function, you know we're working with a graph that is symmetric with the y-axis. And if I say, hey, we've got a graph that's symmetric with the y-axis, you know that we're working with an even function. Those two things are interchangeable. They mean the same thing. But why would we want to say symmetric with the y-axis when we could just say it's an even function? Okay, see how that's kind of shorthand there? Okay, so let's deal with this other one, this other type of example. If I have y equals x cubed looks like this. It goes through 0, 0, goes through 0, 1, or sorry, 1, 1. Let's see, if I plug in a 2, what do I get? 2 cubed is 8. So I'd be up here at 8. So I'm going to label 2, 8. If I plug in a negative 1, negative 1 times negative 1 times negative 1, negative 1 cubed would be negative 1. And if I plug in a negative 2, what do I get? I get negative 8. So I'm way down here. So this is negative 2, negative 8. So here's the graph that I've got. Now, does that display symmetry with the origin? Could I rotate that around the origin, have it look exactly the same? Yeah. Yes, I could. Okay, now, let's see if we can fill this in. If it was even, if xy was on the graph, so was negative xy. Didn't matter whether you went to the left or the right, you got the exact same y value. Is that true on this? No, but how could we say it? If xy is on the graph, what other point would have to be on the graph? Okay, very good. I think I heard it from several of you. Negative x, negative y. So if you go to the right 2 units, you go up 8. Well, if you want to go back 2 units, you just have to go down 8. You go the exact same amount. So if I go over 1 and up 1, I go back 1 and down 1. So if xy is on the graph, so is negative x, negative y. And let's see if we can fill this part in. This means that f of negative x is the, well, it's not the exact same, it's just exact opposite. It's the exact opposite. So if you were expecting a negative, you'd get a positive, and if you were expecting a negative, you'd get the opposite. You'd get a positive, okay? How could I say it here? Now here we said f of negative x is exactly the same as f of x. I'm expecting the opposite. How could I say that? I'm expecting the exact opposite of what I got when I plugged in an x. Negative f of x. Very good. Okay, that's what it is. Okay, now, if this one was called an even function, if that's our verbal shorthand for symmetry with the y-axis, what do you suppose our shorthand is going to be for symmetry with the origin? Odd. Okay? So an odd function, that just means it's symmetric with the origin. So again, if I say odd, you know we're talking about something that's symmetric with the origin. If I say we've got a function that's symmetric with the origin, you can say we're dealing with an odd function. Okay? Now, I'm going to finish with this point right here. What if I said I had a graph that was symmetric with the x-axis? We've got origin, we've got x-axis, we've got y-axis. Why wouldn't we want something that's symmetric with the x-axis? Jessica? It's not a function. Okay? If the top part is the same as the bottom part, if they're right on top of each other, there's no way it could be a function because it wouldn't pass the vertical line test. You with me there? So it's not that we don't care about that type of symmetry. It's just that it doesn't come up very often because we deal with functions more than we deal with things that are not functions. Okay? All right, so that's where we're going to pick up tomorrow. So 3.2 is officially assigned. Remember last Friday I said, we haven't done it all. You could start it. Okay? It's officially assigned. It'll be due 2 days from now, so it'll be due on Wednesday. Does that mean you do it on Tuesday night or Wednesday morning? No. Go home and get it done. Okay? By the way, where are we meeting tomorrow? Karchner's room, room 25. Thanks.